Assalamualaikum warahmatullahi wabarakatuh. A very good day to our lecturer Dr. Ahmad Hussein Abdul Hamid. My name is Muhammad Hafizuddin bin Zainuddin, one of the group member in group 5. So today we're going to present about our aerodynamics mini project where the title is Design and Evaluation of a UAV Cloud Seeding Application. Hope you enjoy. Next, let's get to know our group member. Our group is group 5 with a total of 5 members who is me, Muhammad Hafizuddin bin Zainuddin, Muhammad Nur Syafiq bin Nur Izan Zaini, Muhammad Hadif bin Muhammad Hatta, Nabil Faza bin Muhammad Effendi, and finally Nick Muhammad Haikal Ashraf bin Nick Badrishah. The leader of our group 5 is Muhammad Hadif bin Muhammad Hatta. Next, let's look at the introduction of this project. One of the common usages of UAV in Malaysia is cloud seeding application. Cloud seeding is a weather modification technique that artificially adds condensation nuclei to the sky, giving a base for snowflakes or raindrops to form, improving a cloud's potential to generate rain. This way, it can help Malaysia to avoid drought and water supply problem when there is no rain had happened for a few days or weeks. But the cost for this operation is really expensive. Hence, this project is to design an analysis to cut costs for this operation. Let's look for some examples of cloud seeding UAV. The two figures below is some of the existed cloud seeding UAV. The first one is Cessna 210, which is a common UAV in Malaysia. For the next one is Cessna 441, which is one of the UAV in the United States that used for cloud seeding UAV. The other name called for this Cessna 441 is Conquest 2. Next, the problem statement for this project is the cost for cloud seeding operation is expensive. Mostly, the cost of this operation is expensive because of the design of the UAV. So need to study the design of the UAV to cut costs without lowering the performance of the UAV. The main focus design is on the wings and airfoil. The design must follow proper analysis to meet the operational requirement. There are three objectives of this study. The first one is to design an UAV that can carry the task of cloud seeding operation. The second one is to reduce the cost of cloud seeding operation. And the third and final objective for this project is to minimize the risk of flying conventional aircraft. Next is the significance of this project. The significance for this project is the findings of this project will redound to the researcher who are considering designing an UAV aircraft. The airfoil analysis will be investigated in depth for wing design based on mission requirements. The research will be guided on the analysis of airfoil and design of the wing through advanced software such as SFLR5 and VSP Aero. So this is the mission requirements for this project. For the first part is for the cloud seeding UAV specification. For the total number of flares, the value is #6. The weight of single flare is 1.5 kg. The UAV empty weight is 30 kg. The fuel weight is 11 kg. The maximum takeoff weight or MTOW is 50 kg. The endurance is 3 hours. And the cruising altitude is 9,000 feet or 2,743 meters. And finally, the cruise speed is 100 km per hour. Next is the cloud seeding UAV mission profile. As you can see from this figure, from 0 to 1 is the warm-up and takeoff. For 1 to 2 is the climbing stage. While in the middle of 2 and 3 had a cruise and loiter. While 3 and 4 is the descending and landing of the UAV. So this table shows the aerodynamic design requirement. From this table, you can see the angle of attack during cruising is 3 degrees. The wingspan is 3.7 meter. The wing area is 1.5 meter square. The chord length is 0.41 meter. The aspect ratio is 9.1, and finally the wing loading is 32.895 kg per meter squared. Next, let's look at the aerodynamic design requirement. From the left part is the cruising lift coefficient is estimated by using the CLC formula, where you can get the CLC is 0.15. For the right part is the safety factor. The minimum lift coefficient can be calculated with the formula below, which is the CLC will get 0.19. That is all from me. Next, I'm gonna give to the next group members to present their parts. Thank you.
Hi, Assalamualaikum. My name is Nimam Waika Ashraf and I will talk about the airfoil selection by using perf chart method. We have chosen three types of NACA airfoil for analysis to select the best to use for our UAV. The three types of NACA airfoils are NACA 4415, NACA 23015, and NACA 23018. So, every airfoil has a distinct function. To acquire the proper design of wings, it is critical to discover the right NACA. There are 13 criteria that were used for scoring the airfoil. Each of these criteria is important, whether the airfoil is suitable or not to use in our wing design. To summarize the table, NACA 4415 wins with 7 score, followed by NACA 23015 with 6 score and NACA 23018 with 2 score. Take note that some of the criteria involve CL cruise, which is 0.15, that has been calculated in previous section. So this is the shape of the three selected airfoils that we have analyzed. In our project, based on the score, we have chosen NACA 4415 for our UAV project. Next, Mr. Shafiq will explain the graph plotted based on the analysis by using SLFR5 software.
Based on this graph shown, the CL versus CD for the airfoils, two CL lines have been constructed in order to pick the appropriate airfoil, which are CL ROC max and CL for target cruise area. But for NACA 23015 have the most potential, which the lowest CD, which is 0.0693, compared with NACA 4415 and NACA 23018. As seen by the straight line in the graph, the drag bucket generated from the display graph is in the intended CL. The largest drag bucket is created by the wing and will be located between the axis and the cruise position. The graph of CL against angle of attack, which is important information of airfoil study. When compared to the other airfoil, NACA 23015 produced the greatest maximum CL of 1.6367 and has exceptionally soft stall characteristic. The second best plotted graph comes from NACA 23018, which created a medium characteristic while reaching the highest CL of 1.6178. This findings aid our team in narrowing down the airfoil option based on lift coefficient and stall characteristic. This graph shows the CM in respect to the angle of attack for the airfoil. NACA 4415, which CM which is negative 0.0972, has the lowest CM cruise. The second lowest CM was obtained at NACA 23015. Trim drag can be reduced by using the lowest moment coefficient. The team may use the produced graph to find the optimal moment coefficient for the airfoil. In addition, the lift drag coefficient ratio, which is CL over CD against angle of attack, has been displayed. Based on this graph shown, the CL over CD against the angle of attack. From the graph, the highest CL over CD max is 123 at the NACA 4415. The largest CL max result in either lower stalling speed or higher payload weight at the same speed. Finally, the greatest overall desirable properties for an airfoil are NACA 4415. After NACA 23015 and 23018, the airfoil always got the second and a third best result from the display graph respectively. As a result, our team has obtained to choose NACA 4415 as the optimal airfoil for the Planet Wing.
Assalamualaikum warahmatullahi wabarakatuh. My name is Roman Hadif bin Muhammad Hatta, and today I will be present about wing design. In our project, the design of the UAV is based on a literature review that made in the past section. The dimension of the wing, shape and unique features are designed based on the requirement of the project mission, which is cloud seeding operation. The wing design procedure is shown as a figure below. The first one is we must select the number of wing and proceed to determine vertical location, select sweep dihedral angle, select wing parameters, determine wing effort section, calculate lift, drag and pitching moment, and we'll proceed and if the requirement satisfied, we proceed to optimization and the calculation. If the requirement is not satisfied, we have to select the number of wings again. For our wing design, we have chosen straight type wing swap as our main wing design. It is because the airflow for this type of wing is relatively low and all the airflow will flow above the wing. The, this type of wing design is tapered at chord variation along the span. By tapering the wing, it can cause decrease in drag and increase in lift, which is good for our UAV when in cruising mode. The span of our main wing design is 3.7 meter. The area is 1.5 meter square that that we get from past study and also requirement. The area also used for calculate CL cruise in calculation part. The wing aspect ratio is 9.1, which is quite high. This aspect ratio is selected because it is suitable for long endurance flight or long range cruising. This is due to less induced drag generated from the high aspect. Next, we proceed to tailwind design. In our tailwind design of our UAV, we have designed an inverted V-tail wing shape. The design of our tail wing is due to the effect of the free stream disturbance that may cause upward wings or crosswinds, which is affected the aircraft stability. Therefore, an inverted V-tail wing was selected, favoring for stability in crosswind. The effort for tailwind is choosing to be NACA 0012. This NACA 012 was chosen for being ideal for this type of empennage, for producing slightly lower drag and sufficient downforce to ensure longitudinal stability at low attack angle. The span of the tailwing is 1.7 meter. The area of the tail is 0.55 meter, and the aspect ratio estimated to be 2.6 based on the literature review.
Assalamualaikum. Next, let's look at the UAV concept generation and selection. The selection method that has been used is the push chart selection method. As you can see, there are one datum design that will be selected from another 4 UAV design from past projects that have been searched and studied. For the first one is Ultrunina UAV, the second one is R11, the third one is RC Phoenix, and the fourth and final one is the ASCE UAV. As you can see from this table, the score will be given based on the selection criteria that have been listed on this table. Based on the criteria chosen, the better the design, a score will be given by putting a plus sign to the design, while if the criteria is not good, a negative sign will be given to the design. The sign S is for a neutral score for the design. The design that had most positive side score will be the datum for this project, and as you can see, the Urchunina UAV got the top score, which is 2 positive sign. The table also show the influencing criteria for above character design. Besides that, each design also had the specification as the requirement specification for this mini project. So this is the final UAV concept design for our mini project. The design is based on the datum that had been chosen from the push chart selection method. As you can see, this is the main wing tapered with the AR equals to 9. And the boom mounted inverted V-tail had been used for this final UAV concept design for our mini project. From this figure, we can see the top view the front view and the side view of our final UAV concept design.
Assalamualaikum. My name is Nabil Fazza bin Muhammad Effendi, and I'm presenting the result and discussion of UAV analysis. For this section, the result from the BSP Aero test for Kunina UAV will be presented. The data obtained are plotted from the lift coefficient versus angle of attack curve, the drag coefficient versus angle of attack curve, the pitching moment coefficient versus angle of attack curve, drag polar, and lift to drag versus angle of attack curve. We proceed with the lift coefficient. So the lift coefficient CL versus angle of attack alpha are shown in figure in this slide. Based on the result, the value for lift coefficient very consistent increasing as the value angle of attack increases until it reached the maximum point of 35° angle of attack, and the graph will slightly decreases. The maximum value of lift coefficient produced is 26 lift coefficient. We proceed with drag coefficient. As shown in the figure in the slide, it shows the drag coefficient versus angle of attack. Regarding the drag coefficient of the UAV, the curve increases with an increase in flight velocity and angle of attack. This is mainly since the lift-induced drag increases with an increase in generated lift, and a greater amount of lift is generated by increasing the angle of attack as well as the airspeed. Then we're looking at the lift drag. Lift to drag ratio versus angle of attack curve are presented in figure in this slide. The curve shows a maximum value of lift to drag ratio about 9 to 10 at angle of attack 11°. This angle of attack indicates the optimum flight configuration for the UAV. Next, we proceed with lift coefficient versus drag coefficient. The drag polar lift coefficient versus drag coefficient curve can be seen in figure in the slide. The curve shows the value for drag coefficient at 0 lift is approximately at 0.03. This is the minimum drag coefficient of the lift at 0 lift, and it is also observed that at high angle of attack, it may have larger drag, but at the same time, it can generate higher lift. Next, pitching moment coefficient. The curve of pitching moment coefficient versus angle of attack is presented in the figure in the slide. The curve shows at angle of attack 0°, it's slightly negative pitching moment that gives a tendency to nose down at 0° angle of attack. As for conclusion, this project is successful in terms of the design and analysis of UAV that was designed to cloud seeding operation. The airfoil analysis selection must be completed before the UAV design is revised. In this project, 3 airfoil had been used to conduct in XLR5 software, which is NACA 4415, NACA 23015, and NACA 23018. After running the program, NACA 4415 is the best selection out of 3. There are 4 design selection for the UAV design, and the best selection is Kunina UAV. We select by using part chart method. Based on the results All data obtained from the VSP Aero software have been studied and analyzed. The geometry data of lifting surfaces, fuselage, engines, motors, propellers exported from OpenVSP. The UAV can achieve stall angle at angle of attack 35 degree. The maximum lift to drag ratio obtained is approximately 0.1 at angle of attack 10 degree. For drag coefficient, the lowest drag coefficient occurred at the early stage angle of attack is angle of attack -4 degree. Lastly, for the lift to drag ratio, the highest lift to drag ratio occurred about angle of attack 12 degree and lift to drag ratio 9.5. It shows that the greater the lift and the lowest the drag make, the UAV have a high tendency to fly with better efficiency. That's all from us. Thank you.